Hello everybody. My name is Siddharth, and this video is brought to you by Asha Akanksha Foundation. In this video, I will be discussing the sequence alignment problem, and yeah, it is an important problem. You will see the importance of this problem after you solve it. So, first of all, I will be discussing what is the sequence alignment problem and what are the several techniques of aligning two sequences and what is the DP approach and how to construct a recovery algorithm for that. What is the time complexity? What is the space complexity? And all these things. So let's get started. So first of all, we are given first of all the sequence alignment problem. We are given two sequences. What are sequences? Sequences are any two words, any two words or any two collection of characters in which you can at least determine that two characters are equal or not. That is, A is equal to B or any star is equal to or something. You can determine those things. Now we have to arrange these two words in such ways such that equal characters in these words they get aligned with each other. That is, equal characters in these words they come on top come besides each other. One comes up, equal word comes above the other equal word, such as this way. In this case, O is coming above O, C is coming above C, and in this way if you align, yeah, just these are just two things, two words put together by themselves. So you will see that if you align these words in this way, then there are overall six mixed matches, and one character is aligned with a gap. You can see that. But there is a better alignment, that is, you align these first two in the same way. But R here can be aligned with R here, U here can be aligned with U here, this R can be aligned with this can be this A cannot be aligned with E, but N can be aligned with N, C can be aligned with C, E can be aligned with E. So in this way, we get this alignment. In this way, there is a character C which is aligned with a gap, and there is a one mismatch. And but there is still a better alignment. That is, in this case, you can see that there is a character that is aligned with a gap, and there are two characters which are mismatched. So suppose that we can afford a gap, but we cannot afford a mismatch, because a mismatch basically represents an incorrect thing. That is, two things which should not have been aligned. They have been aligned with each other, and this is an incorrect thing. Whereas something aligned with a gap doesn't really mean that much, and hence we can just this C aligned with a gap can be accepted, but this A and E aligned with each other, these cannot be accepted, and hence we can just increase the size of both of the words, and we can accommodate this in this way. In this case, there are three gaps. So this is the history of the sequence alignment problem. This is used in computer science with biology, computational biology, and this sequence alignment problem is useful in the genetics as well. So let's start our DP solution of this problem. Let's get started with that. So first of all, let's identify our inputs. In the inputs, we are given two strings, capital X comma capital Y. Capital X can be written in this way, x1, x2 up to xm, where xi is a character of a capital X word, and similarly this can be written in this way, where yi is a character of capital Y word. Now you can see that the size of this capital X word is a small m, and this capital Y word is small n. Now let's define two things, that is alpha a comma b. That is, first of all, this is a constant which is greater than equal to 0, and this is the value, this is the cost when A is aligned with B. This is the cost when A is aligned with B, and this is alpha gap, which is greater than equal to 0, which is the cost when a character is aligned with a gap. Now this alpha A comma B is equal to 0 when A is equal to B. That is, two same characters are aligned with each other, and hence this cost is 0. If there is a mismatch, then this is a positive number, which is A is mismatched with B. And alpha gap is equal to 0 if there is no gap. Otherwise, this is equal to the its corresponding constant value. So in the end, we have to output two strings, x cap and y cap, where x cap is equal to x plus some gaps interspersed in between. मतलब x है, x के अंदर कहीं पर भी gaps हो सकते हैं. X can have gaps somewhere, anywhere in between, in any random fashion. Similarly, we have to output y cap as well. Now the thing is that after being aligned, both of these strings will have equal lengths, say L. Now we have to output these two strings, and we have to minimize this particular value. That is, this value is this thing. That is summation of r is equal to 1 to L alpha x cap r and comma y cap r. That is, we are just traversing over the entire strings of from 1 to L, and we are comparing each and every characters corresponding characters of both of the strings, and we are just taking the summation of this value. Now this particular alpha value will be equal to 0 if both of the characters are aligned with each other. That is, both of the characters are equal to each other. If there is a mismatch, then it will have a value equal to this. That is alpha x cap comma y cap and this particular constant, which you can define for any any types of mismatches. And if either of these characters is a gap, then we can just simply take this alpha value is equal to alpha gap. Suppose this is an example. These are two words, AGGTC, ACG, gap C. This is the overall alignment. So in this way, in this case, the overall cost of this alignment will be G is mismatched with C and T is matched with a blank. So alpha gap comes from here, and alpha GC comes from here. And for all the alignments where the similar characters are aligned with similar characters, the alpha value is equal to 0, and hence this is the cost of this alignment. And this particular value represents the cost of x cap being aligned with y cap, and we have to minimize this cost. Now, this is what our problem reduces to. So let us identify the subproblem by thinking about the optimal solution. These are two strings. These are our final two strings, x plus some several gaps in between, and similarly like this. Now, now we will start seeing the characters from the right hand side. We will take in the original string, in the final string x cap comma y cap. We will traverse it from the right to left. We will continue seeing the last characters. What can be overall scenarios for these last characters? Either they can be the same, that is xn and yn, or x can be aligned with a gap, or ym can be aligned with a gap. So how many possibilities can be for the end position? Either xn is aligned with yn, or case 2 can be xn is aligned with a gap, or case 3 can be that yn is aligned with a gap. These are the three cases. That is, now we suppose we do define two strings, x cap is equal to x minus xm. That is, we just take capital X, original X string, and we remove xm from the last of it, and now capital X dash is equal to x1 to x m minus 1. Similarly, we do the same for y dash. Now these are two the other strings that we obtain from removing the last character of x and y. Now for these strings, uh, there can be three scenarios. When we are considering the traversal from right to left, where we are always including the where we are always comparing the last characters of both of the strings, we are always ending up with three guesses. That is, xm can either be matched to yn, that is whatever these strings may be. The last character is aligned in whichever index we are. Suppose in the capital X string, we are at the mth index, and in the capital Y string, we are at the nth index. We compare the xm and yn element, and if they are matched, then the residual align. Then if they are matched, then the cost is equal to zero of this alignment, and we align them with each other, and the remaining string becomes x dash and y dash. So the residual alignment is equal to the optimal solution from the x dash and y dash. Now we have to align the residual strings, and this one is aligned. Now in the final string, that is x cap and y cap, either it can be the case that xm is matched to gap, xm is matched to a gap. That is, now we just align xm with a gap, and the residual alignment is an optimal solution. We take x cap here, but in this case, as there is no character of y included. Why? Because as there is no character of y included, because this is a gap, this is not a character in the original string. Why? This is a gap, and hence this does not count as any character of y being included, and hence the residual alignment is the optimal solution of x cap comma y. Similarly, when yn is aligned to a gap, then we take this, and the residual is the optimal for x comma y cap. Now this is a substructure, and then now we will be proving why this recursive substructure is true. Suppose I will be proving the first case, that is suppose, and the rest of the part can be proved by you. I think you would have understood it by now. So the case one is if the xm is matched with yn. If the xm is matched with yn, then optimal x comma y. Suppose optimal x comma y is the overall optimal solution from the original strings, and xm is matched with yn in that particular string, xm being the last element of capital X and ym being the last element of capital Y. Then the residual alignment is a optimal x cap comma y cap. X cap is this and y cap is this. Now we will prove this by contradiction. Suppose, what are we contradicting? First of all, we are contradicting that this particular opt x cap comma y cap is the which is the residual alignment. It is the optimal one. We are contradicting this thing. Now, first of all, by contradiction, suppose that this thing is not true. We are given with an residual alignment x cap comma y cap, and opt x cap comma y cap with a cost capital P. This is not the optimal one, which means that there should exist another optimal alignment, because if this is not an optimal alignment, then there should be another alignment which is different from this alignment x cap comma y cap, and it is an optimal one. That is, there exists a different alignment with cost p star, and suppose the cost of that alignment is p star, and p star and for x cap comma y cap. Now you would be wondering that how can we get two different values for the same strings x cap comma y cap. Now opt x cap comma y cap is one alignment, and this thing that we are considering for the a contradiction, it is another alignment. That is, it is another way of arranging the same x cap comma y cap characters, and this is another way of arranging the same. So this is the difference. So let the residual align. Yeah, this opt p opt x cap comma y cap. This cos p, and this contradicting different alignment at this cos p star. Now suppose now this is the optimal alignment. Now we append just xm comma y xm and yn in front of this alignment in whichever it is. So what is the cost of new alignment? The cost of the new alignment will be p star. Originally the cost was p star. Now the p star plus alpha xm of yn. And similarly, if we do the same for this particular alignment, then this thing the its cost becomes p plus x alpha xm comma yn, and as p star was less than p because it was the optimal one and p was not the optimal one, so this entire thing should be less than this entire thing. But you can see that this entire thing is equal to after x comma y only, which implies that there is another alignment which is even optimal, even better than this opt x comma y alignment. But we originally assumed that opt x comma y is an optimal alignment in itself, and the alignment obtained after removing the last characters from both of the x comma x and y, it is not an optimal, but opt x comma y is optimal. So this gives us a contradiction because we are getting a better alignment than the opt x comma y, and hence this gives us a contradiction, and hence we can say opt x dash comma y dash is also an optimal alignment. Now let us consider the recurrence. Let us consider the subproblems overall. In the we have opt xi comma yi, opt xi comma yi, where xi is the ith index in the original string x, and yi is the original index in the original string y, and opt xi comma yi, it is an optimal alignment of substrings x1 to xi and y1 to yi. Now what is first of all, yeah, remember this thing that this opt xi comma yi, it gives us an alignment. This is a function that gives us an alignment, that is an arrangement, and it takes two inputs xi and yi, which are several which are subparts of the original strings capital X and capital Y. Now we want to solve opt xm comma yn. So how will we do that? This is the optimal. This is the recurrent structure. So opt xi y and yj, xi and yj is equal to minimum of opt x. Suppose that this is the first case where the last element of both of them are aligned. There the cost this will be considered alpha xi comma yj. Yeah, we defined it in this way, and the residual string is xi minus 1 and yj minus 1. If the last element of yj is aligned with a gap, then we take residual sorry, if the last element of xi is aligned with a gap, then we take the alpha gap because because the last element is aligned with a gap, and we take this residual alignment. We remove one element from the last of xi, which gives us xi minus 1 and yj. Similarly, we do this is the vice versa case, that is case 3 of the same problem. Now this leaves us with base cases. Suppose we will keep on reducing the indices in in this way, and at some time the index reaches 0. That is, suppose we take the example that it reaches xi comma y0. What is the meaning of y0? We remember that the characters are numbered from 1 to n, and similarly from 1 to n. So 0 doesn't means anything. So that uh, this implies that this is an empty string, and which means that all of these remaining characters are aligned with gaps only, and which means that the cost is overall alpha gap into I. Similarly, this is the vice versa case. This is the visual representation. These I characters are aligned with gaps, and this is the now. Now let us discuss the algorithm, the DP algorithm. We will be directly discussing the iterative one. Now consider two arrays. Uh, two arrays. Now consider a matrix. Sorry, a 2D matrix, or which row's index is from 0 to n, and was column index from 0 to n. And we first of all for we initialize these cells is equal to j alpha gap, j into alpha gap, because j is equal to 0 to n, and this 0 comma j is equal to j into alpha gap, because this is the base case when one of the index is 0. And similarly we do this as the vice versa case, where opt I comma j represents the same thing here, where yeah, we are just not saying it as xi and yj, we are just representing the indices. So then we will go from up to down and from left to right in this particular matrix. We traverse in this way, and we fill the opt ij in the same manner as discussed earlier. So first of all, you must remember that to fill any ijth element, that is this element, you you can either want I minus 1 or j minus 1 cell, that is this diagonal cell, this cell, or you can want I j minus 1 cell, that is this cell, or I minus 1 or j cell, that is this cell. That is to fill this particular element, you must have the values in these three other cells only, and you don't want anything other than that from this matrix. So this is a thing that you must remember. So what is the runtime of this particular DP? It is theta of m into n, where the space complexity is theta m into n. Why the reason for space complexity being the size of the matrix, which is the main thing that which is the main variable thing that takes us this much size in the overall problem, and the time complexity being theta of m comma n, because we are in the end traversing each and every cell of the matrix, and that's why m into n. And to fill each and every cell we take order of one time, so that's why. Now we will reconstruct the solution. First of all, before reconstructing, the original solution will be at the opt m comma n position. So we will now reconstruct the solution. That is, we will uh, find the overall alignment after we get opt m comma n, which gives us the cost of aligning both of the original strings x comma y into new strings x cap comma y cap of length L each. Now, yeah, this is the overall pseudocode. You initialize I equal to m and j equal to n. Now, if we over continue until I or j becomes 0. If of ij, now for the current element, you have to find where did its value come from. That is, from in this recursive case, from where, which part of this recursive case did this value came from. you will find the value, and you will find which is the minimum of this value. And you will get that where did this value came from. Now, if ij came from I minus 1 and j minus 1, that is this particular case. This was the case 1, which meant that xi was matched with yj. And similarly, now we will iterate I equal to I minus 1 and j equal to j minus 1. Similarly, we can do for all other things as well. If either I becomes equal to 0 or j becomes equal to 0, then we can just pad the remaining elements with the gaps only. That is, we can pad from x1 to xith elements with gaps, or y1 or to yith element with gaps. So this is the thing. Now remember, I discussed that I said that to fill this I comma jth element, you only need to have these three other cells only. That is, in the entire matrix, you must need only to fill this particular row. You must to fill any cell of this row. You must have first of all the entire the left row left to it, as well as you must have the column to the above of it. To fill this particular cell, you must have filled the column to the left of it, and you must have filled the subpart of the column to the above of it. So we will do space optimization. That is, if we are not even interested in this thing, that is recovery, then we just need to maintain two arrays. That is the arrays for these two things only, and we don't need to even maintain the array for memoization for the entire thing. And these should correspond to two columns. Old should be this one, this column, first one, and new should be current column, that is this one, in which we are filling. And then the time complexity will become order of m min m comma n space, the space complexity, and this is the space optimization. So I hope you understood it. So that's the end of the video. I hope you understood it. In the next video, we will be discussing the binary tree optimizations. So thank you.